review. So does anybody have, I'll leave my purple marker. What's my purple marker? Let's see if any of these markers are good, because I might need a marker. That's decent. No. Okay, so I know there was a question that okay and Ruth had, and then I'll field questions. And if we run out of questions, then I will just start with this stuff where we left off from class. So what was y'all's question?
It was on the name. One for example was two of them.
Ask.
The naming binary compounds we were in textbook problems.
Right.
And like on the first one, you put the dye in front of sulfur, which we did that right.
SCl.
It was
S2Cl2.
S2Cl2. So how to name a compound like that?
Well, we got those right, but then it had ICl. Is that three?
yeah, and
Three. And we got that one wrong.
ICl3.
Yeah.
So what did you write?
The first one,
I did for it. So I think it was
I tried to put mono in front of iodine.
Right.
And then trichloride,
Uh-huh.
and that was wrong.
Right. So you omit mono. So the same way when we're writing I here, we don't include a 1 as a subscript, just because writing I in and of itself is indicative that there's one iodine. Okay, so when we're writing the name of it, remember the formula for naming binary compound, sorry, is you're gonna write the prefix and then the first element, name, and then you'll write the prefix for the second element. Okay, and then you'll write the element name. Then you change the name ending to IDE. Okay, that's the second. So you write the prefix, first element name, you write the prefix for the second element, and then you write the name of the second element with the IDE ending, unless, okay, the only is you omit mono. So this is kind of a foolproof formula for writing names of binary compounds, okay?
Is that even for the second prefix? Because the other one was ICl, and it says it's iodine, but it had monochloride.
So the one thing we talked about, that's chapter 4. What is right here? Okay, right here. So on rule 3 here, we said the prefix mono is omitted unless being used to distinguish between compounds with the same element. So there you had ICl3 and ICl. Okay, and so there they are putting the mono in for that second element name. Sometimes they'll include it right here. If like another good example is carbon monoxide versus carbon dioxide. If you're dealing with the same element, you name both. Then I would say, oh, that one's a tri and that one's a mono, okay? Otherwise, you don't have to include mono, okay?
So only when if in the equation there's two of the same.
Right, and so I don't want to, don't worry too much about mono. Just stick with the rules that you know. I'm not going to put two identical things on the exam and say name both, okay? Which is when you would need to include mono, but you'll just have to know the general rules for naming binary compounds is what I'll have on the exam. Okay. Okay, was that it?
Yes.
All right, any other questions?
Can
Grace?
we do some practice mole ratio problems? Because I don't really understand mole ratios.
Okay, yeah, we sure can. Let me actually jump back over to
I have a hard time with the grams of something, like grams to grams.
grams to get the 3-part problems. Okay, let me see. This was balance. So what we'll do is we'll go ahead and balance this one, and then we'll do a mole to mole ratio problem, and then we'll answer it's a redox part too, so we'll get some practice with redox, and then oh no, right here. This might answer almost both of y'all's questions with this one right here. And then this one also down here is a 3-part problem. So why don't we just work through some of these things, and that will help with some of the chapter 6 stuff. Also, are y'all warm in here? There's these, okay, they're kind of loud. So can y'all open the back panels? Yeah, that one right there. Don't worry, no spiders. Yeah, you push down on one side. Okay, like the top and bottom. There you go. We can get some air in this one right here. Okay, I don't know, is that cold air?
That's cool.
Turn that off. Down cold?
Yeah.
All right, that should help. So it's gonna be kind of loud, but. Are you gonna freeze? There's a chair up here if you need a. Okay, so I'm gonna start with this one. This one actually won't answer your question yet, Grace, probably until we get to the next slide, but I think this is a really good practice problem for you guys. Come on in. We got two up here if you need one. All right, so MnO2 plus HCl makes MnCl3, or sorry, Cl2, chlorine and water. Okay, so this is magnesium oxide and, sorry, manganese. Manganese, not magnesium. Manganese is Mn, magnesium is Mg. So manganese oxide. So manganese is actually a transition metal. So it's hard to actually know. We got to figure out what's kind of our oxidation number going to be on manganese. That's going to be one of the hardest parts of this. So, so first balance it, and then it's a redox. So we're going to figure out which elements oxidized and which ones reduced. And so what should we do to balance this real quick? They'll think. Right, so our oxygens, at least so we got 2 on the reactant side, 1 on the product side. So if we put a 2, try a 2 right here in front of water, maybe that will help. 4 on HCl, Ethan said, because you notice there's 4 chlorines on the product side between our 2 products total. So we'll need 4 on the other side. So now we got one magnesium, or I keep saying one manganese, 2 oxygens, 4 hydrogens, and this makes 4 hydrogens, and then 4 chlorines. So I think we're good. Okay. So like right now, Grace, if I said you only have 3 moles of HCl, how many moles of chlorine would you get? So if I said that, like, right, you got, once you have your balance reaction, then you can work a mole to mole ratio problem. Okay, you gotta have a balance reaction first. So we see that it takes 1 mole of manganese oxide plus 4 moles of HCl to give us the set ratio of products. If I said we only have 3 moles of HCl, then what you would start is you would start with that 3 moles of HCl. Okay, you would multiply by your mole ratio. You want to cancel moles of HCl. You want to convert to moles of what I say, chlorine. Okay, Cl, and the coefficient there is what? Just 1. Okay, so you would say for every 4 moles of HCl, I want those to cancel. I know that I'll produce 1 mole of Cl2, and I'm just looking at the 4 and the 1 here. I just come in from in the balance reaction, and so then I'll cancel moles of HCl, just like that, and then I would just say 3, essentially 3 divided by 4, so it'd be 0.75 moles of Cl2 would be produced. Does that help? Answer yours real quick. Okay. That's just a side. I just made that from.
How did you get 1 mole of CO2?
When we balance this, our coefficient here was 1. So if I have 1 mole of this plus 4 mole, if there's not a number written, it's a 1. Understood. Okay. So 1 mole of this plus 4 moles of that will give me 1 mole of this, 1 mole of this, and 2 moles of water. Okay. So I said, if I only have 3 moles of HCl, how many moles of chlorine would I get? Well, I know the 4-to-1 mole ratio, and I wanted moles of HCl to cancel, so I put the 4 on bottom.
So the chlorine that we're looking for has nothing to do with the chlorine that's with the manganese.
I just say how much of this would I produce? If I just say chlorine, then I'm just talking about this. This is manganese chloride.
Okay, that's what that.
So I would have to say how much manganese chloride.
Yeah, for sure.
Okay, now this is manganese chloride.
So I was looking at all of the elements for the right one. Even the ones that were.
So we name these compounds individually. So if I just say how much chlorine would I get, I'm just talking about that part. Even though this compound does have chlorine in it, that's not chlorine. That's manganese chloride. Okay, that makes sense? Okay. Now it says, so we did the balancing part. In the redox reaction above, which elements being oxidized, which elements being reduced. So now we need to go in and do what? Yep, oxidation numbers. So anybody want to toss out what do you think oxidation numbers? What should go where? I mean, you can start with the easiest thing. You can start reactive side or product side, doesn't matter. You don't have to necessarily do everything on the reactive side then the product side. You can just do whatever's easiest to you first. No. No, you're not considering the electronegativity chart. So I'll remind you guys of a couple things. Anything by itself gets an oxidation number of 0. We always put, so like if you have right here, this one's gonna be tricky, or it's gonna seem tricky because manganese is a transition metal. But you always give the positive oxidation number to the first element, the negative oxidation number to the second element, just as if it was like a cation and an anion. And then they have to add up to 0, just like in an ionic compound, okay? So it shouldn't feel too foreign.
So when you tell me the transitional metal and with one other element, it's always a new zero, right? Is that what you're saying? That they'll always cancel together now?
They'll always add up to 0 in a compound. That was our rule, right? When nope, down. Right here, okay? You remember the rule number 4, the sum of oxidation numbers in a neutral compound is 0. So unless there is an ion, which we're not going to be on example. So this rule is always going to apply on number 2. Okay. The sum of in a neutral compound is 0. You're only going to work with neutral compounds and reactions. Okay. So every compound in our reaction here is a neutral compound. So, I mean, let's just go through. We know chlorine over here on the product side has what? 0. I mean, let's just start going through this. So manganese and oxygen. So here, I'll help you guys with the first one. Oxygen is always predictable. Okay, it's in main group 6. Okay, so it'll have a -2 charge as an anion. So it's going to get a -2 as the oxidation number here. Now, what you have to recognize, so if this is our negative side of the compound, and then the manganese are positive side of the compound, this side and that side have to, that's what we're saying, have to add up to 0. So we have 2 oxygens, right? So that's a -4 overall. Okay, each one has a -2. So what does manganese have to be? +4. It has to be +4. Who did I just lose right there? Okay. So you have 2 oxygens. So that's like saying -2 and -2. So this, we only have one of these. So this has to balance all of that. There we go. All right, what about H and Cl? Who has those numbers for us? H will be a +1 oxidation number here. Chlorine is a -1. Okay, what about this one? Again, you can divide it up to a positive and negative half of your molecule if you want. Chlorine is going to be -1. We've got 2 of them, so that's like saying -1 and -1. The other side has to balance, and we only have 1 cation here, so that's got to be a +2. Okay, all we have left now is water. Water, the hydrogens are +1, oxygen is -2. All right, I'm going to erase what I wrote down here so that we can actually see what's changing now. So the whole point of a redox reaction, once you get all the oxidation numbers assigned, is you say what's changing, what's becoming oxidized, what's becoming reduced, okay? So what do y'all think? Manganese and chloride or chlorine, okay? So we obviously see the manganese here is going from a +4 and it's becoming a +2 on the product side. And oxygen's a -2 on both sides. Hydrogen's a +1 on both sides. So your chlorine, some chlorines are staying a -1. Y'all see that? Look right there. All the chlorines in HCl are a -1 on the reactant side. Some of them stay a -1, but some of them become 0. That is oxidation. I just told y'all the answer. No, we're not adding any of these together. Okay, don't do that. So I'm just simply observing. I'm saying I've got 4 chlorines here. All of them are a -1. I only have 2 chlorines here. Those are still a -1. So those chlorines didn't change, but 2 of the chlorines are now by themselves. So some of them did change. All right, so even if only some of them changed, that's still, they're all -1, and now some of them are 0. So we would say the manganese is reduced. We say the chlorine is oxidized. Okay. That one's challenging. I think that one's challenging. Okay. All right. It's pretty insane, the more you get into biochemistry, how our body literally lives off redox reactions.
So you don't have to consider the balancing those before and before HCl, like you're not really paying attention to that, it's still for the same thing.
Right. Right. Any questions on this one? It's redox. It won't be any more complicated than that, but I think that one was challenging. Okay. These questions, so we actually worked in lecture, we did, I had this as a 3-part problem, but you can see there's only 2 questions here. So we did the 3-part one in class together. But these were kind of the 2 preliminary ones that I was gonna have leading up to that 3-part problem. So it gives you an equation. This is how rust is made. Iron, when it's oxidized, makes iron oxide, which is your only product here. By the way, what kind of reaction is this? Is it a combination, decomposition? Combination or synthesis, okay? You got 2 things coming together, you get 1 product, so combo. All right, so the first question says, how many moles of rust are made from 7 moles of iron? So what I'm gonna highlight here, I don't know if you can even see that, probably not, I can't see that. Let me try a dark color. Y'all see that? I'm highlighting the 2 units here, because that helps me immediately identify what kind of problem this is, okay? This is a mole to mole problem. I got moles of one thing, I wanna know, this is just the mole to mole ratio, okay? So how many moles of rust are made from 7 moles of iron? We're gonna start with 7 moles of iron. And which one is rust? So I know that this one right here is iron. Which one's rust? Product. So I'm interested in the mole to mole ratio between these 2 things. So somebody tell me, what do I need to do from here? Right? So for every 4 mole, we're going to multiply by my mole to mole ratio. 4 moles of Fe on the bottom. All right, 2 moles of Fe2O3. Now you can simplify this to this mole ratio right here. This does simplify to well, in the problem 1 and 2, but you don't have to do that. You just plug in the numbers that you have. Don't worry about that. You'll get the same answer, okay? So you'd say 7 times 2 is 14 divided by 4. What is that? 3.5. So 3.5 moles of rust, which is Fe2O3. There you go. Okay, how many moles of rust? Now this next problem is another step at it. So this was a 1-step problem. I say a 1-step problem because I plugged in only I only converted 1 thing. This next problem is a 2-step problem. Because if you look at the units, I'm going to highlight those again. It's asking for moles of rust, but instead of starting with moles of something, we're starting with grams of oxygen. So we're going from grams of one thing to moles of something else. This is going to be a 2-step problem. So I like to go back in. Where did I have it? I had a diagram slide that I always keep pulling y'all back to, right here. It's like you're starting with grams of oxygen, and we're wanting to get to moles of rust. So that's why I say 1-step, 2-step, okay? And then these, you can always break it down. If I have grams of something, I use the molar mass to go to moles. I can make these arrows over here as well. I can use the molar mass to go to moles of that thing. And then if I get moles of that thing, I can use the mole ratio to go to moles of something else. So this will be a 2-step problem. We use both of those steps. Right there. Okay, so somebody tell me how I should start this. Okay, the 83 grams of O2. What's the first thing I need to do? 32, where'd you get 32? So we've got to have the molar mass of oxygen here. And the molar mass, oxygen on the periodic table is just 16. We got 2 of them, so we say 2 times 16 grams is 32 grams of oxygen per mole. Okay, that is the molar mass of oxygen. Sorry if y'all can't see the screen very well. So this is what Atiana just plugged in. So I'm going to divide by this because I want grams to cancel. This is grams per 1 mole, so 32 grams per 1 mole of oxygen. So that's one step. I'm almost there. I'm just gonna keep going. And Fatima says you put in the mole ratio from moles of oxygen, because that's what we have on the top right there. See, grams cancel those out. And then we'll plug in the mole ratio. So what is our mole ratio? The question's asking for rust. So I know that I'm just looking between these two now. So it's a 3-to-2 mole ratio. So I have moles of oxygen on top. So I'm going to say for, what was my coefficient? 3. There it was. 3 moles of O2, because I want moles of O2 to cancel, and 2 moles. I just grabbed that number from the balanced reaction again. Right there. And that's it. So this was my first conversion factor. This is my second. So that's why I say it's a 2-step problem. And then we actually did the 3-step problem in class. What's my answer though? 83 divided by 32 times 2/3. 1.73 moles of Fe2O3. There you go. Okay. And then this one, I can leave that there for a second. This next one is a full 3-step. So we got ammonia, NH3, and oxygen make nitrogen. Here's where I would use the mono, nitrogen monoxide. But they're not going to say monoxide. I'm not going to have that in the exam, but it's an example, nitrogen monoxide and hydrogen there. So how much hydrogen in grams is produced from 25 grams of NH3? So again, if I'm highlighting my units, I always encourage you to do that. If I'm highlighting units, notice that it's asking for grams and I'm starting with grams of something else. This is a 3-step problem. Even if it were to say how many milligrams or how many kilograms, you're still going to go grams to grams and then you'll convert to your kilo or your milli in the end. Okay. So start with the 25 grams of NH3. Oh, first off, we should probably make sure it's balanced because I don't think it is. So what do y'all think we need to do to get it balanced? You said 2, 1, 2, 3. So that gives us 2 nitrogens on both sides, 6 hydrogens on both sides, and 2 oxygen. I like it. Okay. So 2, 1, 2, 3. Those are the coefficients we ended up with. And now I'm just going to follow my diagram through. First, I'm going to divide by the molar mass of NH3, plug in my molar ratio between NH3 and hydrogen, multiply by the molar mass of hydrogen. Those are always your 3 steps. Okay. Anybody have the molar mass of NH3? NH3, we got to add, so it's 14. Nitrogen is 14. We'll just say 0.007. And hydrogen is 1.008. We got to multiply that times 3 though. What is it? 17.031 grams per mole. There we go. That is how many grams of ammonia, NH3, are in 1 mole of NH3. So I'm going to divide by this because I want the gram part. The 17.031 goes with the gram part. So that goes right there. And I'm putting that on my because I want grams to cancel just like that for 1 mole of NH3. So that's my first step. Now what do I do? Okay, what is our mole ratio? We're going from NH3 to hydrogen. Okay, 2 mole NH3 on the bottom. Ariel said put 3 mole H2 on top. Okay, so that's my second step. Last step. We got to convert from moles of hydrogen to grams. So we need the molar mass of H2, which is just 2 times 1.008, which is just 2.016. Okay. So then I'm multiplying by this one because I want moles to cancel. I put the 2.016 part because that's where the grams go over 1 mole of H2. This is H2. Okay, again, let me point out how I am labeling. I forgot to here, but I'm literally writing my compound in every step of the way. I want y'all to do this on the exam. Okay. This is exactly what is no different from the things besides the reaction, I guess. There's no different from what y'all did on the lab last week. Okay. Do have this problem, but does anybody else have any questions first? Any homework problems that y'all wanted to look at? Any? Okay, I see lots of hands. So I don't know who had a hand. I saw Will's hand and then I'll get Alicia. What was your question? Yeah, we did that. You missed it. Oh, which one? This one? This was the first one we did for those of y'all who walked in late. It was a redox reaction. Okay. So we walked through and we took all the oxidation numbers down and we figured out what's oxidized, what's reduced. If we have time at the end, I'll try to do another one. What was your question? Go over what? Sorry, say that one more time. Tungsten problem. Oh, the tungsten problem. How many of y'all hate the tungsten problem? Okay, the tungsten problem. Do you have a textbook? No, it's not on the textbook, is it? It was on so here, anybody have the reaction in your notes or somewhere? It was tungsten oxide and tungsten. Okay. Did it give y'all the balance reaction or did y'all have to balance it? Okay. Okay. So it says, it changes everybody's numbers. Y'all probably picked up on that by now. But let's just say that it says you got 5.45 grams of tungsten. 5.45 grams of tungsten. And then ask you several questions, okay? The first one was how many moles of tungsten were formed? Okay, so it says, it gives you this info in the problem, and it says how many moles of tungsten. And it said tungsten, but you have to understand tungsten is that which you could easily Google in the internet. So what do we need to do here? You're given grams and it's asking for moles. Please, y'all know what to do. No, no. Guys. Let me show you a really important slide. This is why I don't do everything in red, and occasionally I'll put something in red. Okay, I try to make a big deal out of these two statements. Molar mass is a conversion factor between mass and number of moles. Avogadro's number is a conversion factor between moles and number of molecules or atoms. This problem so far doesn't say anything about molecules or number of atoms. All you need is the molar mass, which we get how? Do you even have to calculate it? It's an element. You don't even have to calculate. You only have to calculate the molar mass of compounds. Elements, you look at the periodic table, you say, where's W? Okay, W is like on row 6, right between the TA and the R8. Okay, we find actually 6 on both sides, at the top and on the side, because the row and the column together. There's W, number 7, element number 74. So the 183.84 is the molar mass. So I just take these grams, I say 5.45 grams, divide 183 point, what was it, 84? 4 grams per 1 mole. Having an extra L today. Okay, so y'all help me. I know when you're doing it on your own, it's different than when you're in class and I'm walking you through it. So I get that. You don't have to have had years and years and years of chemistry. I'm not, I don't expect that, but what's confusing to you guys when you read that? You're like, I don't know where to start. So I can pinpoint that, maybe I can help redirect.
I could write 183.84 by 5.45.
Okay, so let's walk through. What if you accidentally took 183.84 grams, which is grams per mole? You have to understand these two units, when you're working with a molar mass, are inseparable. You can't just write 183.84 grams. That's how many grams of tungsten are in a mole. So those units always go together. So if they're inseparable, I have to write it over 1 mole. So when if I go to do 1 over, divide by the 5.45 grams, sure, your grams cancel, but what kind of answer are you left with? Not moles, not units of moles, units of 1 over moles. You have to understand or recognize, no, that's not what I want. I want moles, not 1 over moles, okay? So thank you, because you're probably not the only one who tried that.
Okay, but what I'm hearing the problem with is when I look at a problem and I can't tell whether or not when to use the mole ratio. Like, I don't know when to use the mole ratio.
Okay, let me just go back to. Like the problem we just worked here. Here is why I highlighted these units. I have a problem that says how many moles of brass are made from 7 moles of iron. If those are the only units, like it gives you units of moles for one thing, and it's asking for moles of something else, then you have to use a mole ratio there. That's the simplest kind. If it also, next problem down, what we just worked. If it gives you grams of one thing and asks for grams or milligrams or kilograms, if it's a mass to mass conversion. Mass of one substance and you want the mass of another substance, whether that is the reactant or the product, doesn't matter. You will have to use a mole ratio. Why? Because that automatically puts you in that 3-part problem, which is, I keep going back to this diagram, okay? When you are converting from mass of one thing, mass of substance A, to mass of substance B, will have to convert between moles of that thing, one thing to moles of the other thing. That's where you have to use mole ratio, okay? Or the other way is if it gives you grams of one thing and asks you for moles of something else. It is just like the oxygen to rust problem we just worked a few minutes ago, if y'all remember, okay? So that's not necessarily a quick answer, but that is how you know when to use a mole ratio. Okay, going back to our tungsten problem here. That was the first part. So let me erase, you don't do this. That was the first part. The second part said, how many moles of tungsten oxide are required to produce this many grams of tungsten? Okay, so the second question, I'll just come over here, says, how many moles of the tungsten oxide? So that is which one? Which one's tungsten oxide? This one right here. Even if you weren't really sure, you could say, okay, I know tungsten's W, I know oxygen's O. That's the only one with W, no, that's got to be tungsten oxide. Okay. We're required to produce this much tungsten. Okay. So here I have grams of one thing. I want to go to moles of something else. So it's like I'm starting here and I got to go boom, boom. All right. I'm starting with mass of tungsten. I first have to get moles of tungsten, then I'll have to get moles of tungsten oxide. That's why I like this diagram so much when you know how to read it, because it tells you exactly what to do. Okay. So I'm going to start with and your number was probably wildly different, but 5.45 grams of tungsten. I'm going to do the exact same step. So the way it sets you up sometimes on these two is your answer to the previous problem is part of your next problem. Okay. So you actually just take your answer here and you do one more thing, but I'm going to set it up, the whole thing, so you see it from beginning to end.
Unless you mess up part A, then the A, B, C, and D are
Right. If you mess up part A, you're screwed. On B, C, and D. So don't mess up part A. Okay. Now, looking at this, it's a 1-to-1 mole ratio, right? Is that what it ended up being? I think it's balanced. Yeah. So just 1 mole So your answer to part A should have been your answer to part B. All right, 1 mole of tungsten, 1 mole. Now, if you're writing it out on paper, I want to see all this, right? That's what I want to see. But grams of tungsten cancel, moles of tungsten cancel. But notice mathematically, this is no different than what we did over here. We just times and divided by 1, which doesn't change your answer at all. And then lastly, I don't know what the last part is.
Because I'm sure I'm off and gave up and cried.
Okay. So I'm assuming it got into Avogadro's number somewhere, asking for number of molecules or something.
Okay, so how do you go from there to this?
How do you go from where to where?
From where we gonna go to Avogadro's number?
Okay, so let me make up a problem where we would need to use Avogadro's number. So I'm not sure, but what it might have done, it said, how many molecules of tungsten oxide would that be? So if you had the 5.45 grams of tungsten, which it gives you in the problem initially, some number of grams, how many molecules of tungsten oxide would that produce? Okay. And so then it's literally the exact same setup, but once you get here, anybody want to fill this in? What's the last thing we're going to do? We have moles of tungsten oxide if we stop here. How do we go from moles to number of molecules? That's Avogadro's number. Do I put it on bottom or on top? Because I know that my relationship says that for every 1 mole of whatever it is I'm talking about, pennies or people or here, molecules of tungsten oxide, it is Avogadro's number of atoms of molecules. Whoops, 6.022 times 10 to the 23 molecules of WO3, okay? So you'll see that the moles cancel. Now again, it had you literally do the problem, I guess, and I don't know what the last part was. It was again what I just did, step by step. But that's the 3-part problem all in one. Well, slightly different than the other 3-part problems. We're going to molecules here versus grams. But yeah, so you multiply by Avogadro number.
So the molecules and atoms is Avogadro's number, and mass and grams is mass, and when you find the mass and the grams, you calculate it. What do you use when you try to find the grams to the molar?
What do you use when you're trying to find the grams and the mole? So like if you're trying to calculate the molar mass of something, you're looking at the periodic table, you're assessing how many atoms you have in your compound, and you're just multiplying the weights on the periodic table by the number of atoms for that element you have. You add up the molar mass that way. If you're trying to, if you're given a number of grams of one thing, it says how many moles is that, or vice versa, you're given a number of moles of one thing, so how many grams is that? That's when you use the molar mass to convert between grams and moles. Okay. Why don't we, Ethan, you had a question?
The polarity right here. Molecules are polar, but
Yeah.
one was 3 of them. I think I know how to do these 2.
Oh, see?
Yeah, like,
Yeah, we didn't actually do that one in class, did we? So this was, well, I have it on my review slides right here. No. Where was it? There it is. So he asked the question about the one we didn't do. But I actually think it was in our lecture slides. Yeah, there it is. That's this molecule right here. Okay, so the formula here is C2H3Cl. I said, is this molecule polar or not polar? So this one right here, we looked at it in class. Basically, when you draw this out, and I mean, you see it, but it's got the carbon-carbon double bond, 3 hydrogens. The only way this could be worked out is, and you could draw it either way, honestly. I could put the chlorine, I could put the chlorine down here. I don't care where it goes. Okay, you just have 2 carbons in the middle. You have your 3 hydrogens arrayed somehow, and you got the chlorine in one corner over here. That's too many molecules. Okay. Doesn't matter if it's drawn like this or like this. Okay, you get the same answer hopefully. You should. So then you start assessing, so the question here is this molecule polar or not? Then you start assessing what kind of bonds do you have. You gotta look at your electronegativity chart. So here's what I see. I've got carbon-carbon bonds. Okay, it's actually double bond, but it doesn't matter. Still a carbon-carbon bond. I've got carbon-hydrogen bonds. And I have a carbon-chlorine bond. Okay? All right, so the way this works, and I'm gonna calculate my electronegativity. I know this one, the electronegativity difference is 0. I tried to break this in lecture that this is always a non-polar bond, a carbon-hydrogen bond. You never should actually even have to calculate that in your head. It's 0.4. That's the electronegativity difference. And carbon is 2.5, hydrogen is 2.1. People look at the chart. So the difference is always 0.4, never polar. Okay, so this is not polar. All right, so but what about this one? When you calculate that, I think chlorine is 3.0, carbon is 2.5. So the difference there is 0.5. This one is your only polar bond in the molecule, okay? So what that means is I'm zooming in right here. I'm looking at that part of the molecule and I'm saying, all right, I got a more electronegative element, plus I got lone pairs all over this thing. So I'm gonna put a partial negative right there. I'm gonna put a partial positive on this end. And then I just draw my dipole, okay? How do I draw the dipole? Pointing towards the CO. I don't care if you draw it across the molecule like that, just so that you tell me that side of the molecule is not polar, this side is. You could just draw it down along this particular bond if you want. Both are acceptable. Is that helpful?
Yeah.
The molecule is polar. The molecule as a whole has a net polarity. Okay, who else had a question? I know there were some other hands. Just that one bond, yeah, and all the lone pairs. Remember, it was you assess your bonds, your lone pairs, and the shape. So we consider the shape. There's no symmetry here, right? There's no dipoles that cancel. We only have one dipole anyways.
So just because that one bond, like it kind of messes up the whole symmetry of it and it makes it polar.
Yeah. Like if this was another hydrogen, this molecule could be non-polar overall.
Right, so if that hydrogen
But
was,
because you got a chlorine here,
yeah.
you got one polar bond, it makes the whole molecule have a net polarity. So
Yes,
yes,
if that chlorine methodology was polar, it was hydrogen, it would be also symmetrical and it would be non-polar.
and all the bonds would be non-polar. So no matter if it's symmetrical or not symmetrical, none of the bonds are polar, no lone pairs, it's a non-polar molecule.
Okay, so we have at least one, like,
You got one polar bond in your molecule, and you have a dipole that does not cancel. That molecule overall is polar. Shayla? Oh, that's what I was gonna get to, but I wanted to stop and fill some questions. No, where was it? Right here. But yeah, I think this is a good problem, even if we didn't work the whole thing, which we totally can. I think a good practice here is it gives you like a word style problem and you have to write the reaction out. Okay? So it says, and it's challenging because we don't know what the heck oxalate is. Fortunately, I would give that to you. Okay. If I needed you to. So you need to make 100 grams of calcium oxalate. Calcium chloride mixed with sodium oxalate reacts to make calcium oxalate and sodium chloride. Should have been working on this on the iPad because I just realized none of the people I watched the recording of any of that from there. Oh well. Calcium chloride mixed with sodium oxalate reacts to make calcium oxalate and sodium chloride. How many grams of sodium oxalate and how many grams of calcium chloride do you need? So there's like a lot going on here. First off, you got to write and balance the chemical reaction. I would explicitly tell you to do that on the exam. Okay. Then there's actually two 3-part problems all within this. Okay. And you would work them almost the exact same way. So we can do one, I think. And then if there's any other questions, I can fill more questions. But basically, let's write out this reaction. It says calcium chloride mixed with sodium oxalate. Those are your reactants, and they react to make, and then it tells you your products, calcium oxalate and sodium chloride. So I'm gonna put an R here for reactant, R for reactant, and then so it's a P product, and that's a P product. So what is calcium chloride? What's the formula for that? Yep, CaCl2. What is sodium oxalate? So here's oxalate. Shows you a picture. This is a polyatomic ion. There's 2 carbons. There's 1, 2, 3, 4 oxygens, and it's got a -2 charge. So how would you write the formula for that? How would I write the formula for oxalate? Yeah, you just write what you see. I got 2 carbons, C2O4, and it's a -2 charge. Does that make sense? That is oxalate. So what it's saying is we got sodium oxalate. So how would you write the formula? I mean, treat oxalate like it's nitrate or carbonate or any other polyatomic. How would you write the formula now for sodium oxalate? Okay, sodium we know is an Na with a +1 charge. And I see that oxalate has a -2 charge. So we're gonna have Na2 and then C2O4. Okay, who have I lost? Put the 2 in front. Okay, so don't worry about balancing until after all that's one of the biggest things I'm gonna tell people. Don't worry about balancing until your formulas are correct. You worry about your formulas, which involve subscripts first. Then once you get all your formulas right, then you go back and balance, okay? If you try to balance and write it, you'll never get it right. All right, now I got 2 ionic compounds here. This is a double displacement reaction, okay? And it tells you what your products are anyways, calcium oxalate and sodium chloride. So we know sodium chloride is NaCl. We know that all day long. And then calcium oxalate, how would I write that? CaC2O4. It's a +2 cation and a -2 anion. So I only need 1 each. 1 calcium, 1 oxalate. Okay, now I can go back and balance. Do I need any coefficients anywhere? Yeah, because I got 2 sodiums here. Put a 2 in front of sodium chloride. I think that's it. I think honestly, that's all I have to do. All right. Okay, so that's the first part of the problem. Here's where the actual questions begin though. How many grams of sodium oxalate? That's one question. Second question is how many grams of calcium chloride do you need? Let's just answer one at a time. It says you need to make 100 grams of calcium oxalate, which is this. So I want 100 grams of this. How many grams of this do I need to start with? Okay, so this is a 3-part problem, grams to grams, grams of one thing to grams of something else. So I'll start with 100 grams of CaC2O4, but I'm not going to get very far because I need to do what next? I need the molar mass of this thing. All right, so calcium is 40.078. So I'm trying to find the molar mass of calcium oxalate. Carbon is going to be 2 times the 12.011. Oxygen is going to be 4 times 16. $128 point what? Am I close or am I off? 128.015. Oh, 0.5. Okay, grams per mole. See this?
Yeah.
Calcium's a main group 2. It's got a +2 charge. Oxalate's a -2. So
Like after you switch, like on the left side, like the sodium has a 2 by it. It because the C204 like switch. That makes sense.
Okay, help me. What? Sorry.
So the C204 doesn't it have like a -2 charge?
Yeah.
And then that would switch over to subscript.
So here okay, I think you're flipping. We needed 2 sodiums here to balance the charge on our anode.
Oh, okay.
But then all of a sudden, we're pairing a -2 anion with this +2 cation, so we just need 1 each over here. So there's nowhere where we need a subscript of 2 on our oxalate or a subscript of 2 on our calcium.
Okay.
Think about it.
Oh, it's just one. I thought it was two. 28.
Oh, 0.150? Oh, 0.1. Okay. All right. I think we're on track now, 0.10. So now I'm going to divide by that, 128.10 grams per 1 mole. And this is all, I'm going to shove it in here, label it somehow, C204. Now, this is step 2, so it's a 3-part problem. Here was my first conversion, converting from grams of calcium oxalate to moles. Now I'm going to go moles of calcium oxalate to moles of what? It says how many grams of sodium oxalate. So I'm going from this to this. And it's just a 1-to-1 mole ratio, okay? Still write it in, don't skip that. 1 mole CaC2O4, 1 mole of Na2C2O4, okay? Last step. And I wanna know how many, it says how many grams of sodium oxalate. So I'm gonna put moles of sodium oxalate in grams, so this is the molar mass that I need of sodium oxalate. So it's gonna be very similar to calcium oxalate, but with 2 sodiums, which I can't even see sodium, is at 22, it's basically 23.0, 22.99. And we got the 2 times the 12.011, and the 4 times the 16. 63 and 64 is 107, no, 127. Anybody got it? It's more, like 150 something. Okay, 63 plus 24, 87 plus 64. $134. Did you forget is anybody double check that? Okay, awesome. 134 point what? 0.002 or 0.22? All right. Okay, so then we're going to multiply by this. So for every 1 mole of Na2C2O4, it's 134.002 grams of your sodium oxalate. Okay, so this is a challenging problem because you got to write it and balance it first. You got to do all that right to even have a chance of getting all this right.
So it's a possibility a question like this gonna be on the exam.
Well, for sure. Why not?
Yeah.
Each of these things you have done individually. It's, I think, putting it all together is what makes it hard. Anybody got our answer? 100 divided by 128? Times 134? Let me pull my calculator out and do this. We got 20 calculators. I'm sweating in here. Is it blowing cold air?
It is 104.69.
104.69? 104.61 grams. All right. So. Now, will there be multiple problems like this on the exam? No. But could there be one? Absolutely. I mean, I've told y'all since we went over mold, I said, you're gonna have a 3-part problem on the exam. So. It is 2:27, so for those of you time wise, I'd have to be somewhere right across town at 3 o'clock. So I probably got 6 or so minutes I can play with, if there are any other questions.
So when you get back,
But-
you'll be free?
Do what?
When you get back, you'll be free?
When I get back, I'll be free, like later this evening?
Like, I'm talking about just to answer emails.
Oh, to answer an email. So my daughter has gymnastics at 4 o'clock.
Yeah.
I can answer emails during that. After I get back from that, it's dinner and bedtime. I'll check my email at 8 o'clock, okay?